in this parenthesis, these quantities are all macroscopic quantity. So what that means is that it grows like the system size n. Okay, and Kb is something that's relatively small, and T is not something that does not grow as you reach the thermodynamic limit. So it means that this integral basically will be dominated by this exponential factor, because it decays really fast when the system is large. Okay, so now we are going to use the saddle point approximation that we have discussed previously when we try to derive the Stirling's approximation. That basically this integral will be dominated by the region with energy E prime that satisfy the condition that the exponent has a first derivative that is equal to 0. Okay. This thing is equal to 0 when E prime is equal to some special value E star. Okay. And you can just take the derivative explicitly, and what you will find is that equal to 0. So the point where this integral is dominated by the exponential factor is when the derivative of the energy with when the derivative of the entropy with respect to the energy is equal to the given temperature T. Okay. So what we are doing here is that we are using the saddle point approximation. Okay. So now we know that the integral is dominated by E prime equal to E star. Which means that the partition function should also be similar behavior, because when we are calculating the partition function, basically this A is considered to be 1, and we are just integrating over this exponential factor. Okay. So I have some mistake. Yeah, it should be 1 over T, sorry. Okay, thanks for the reminding. Okay, so now the point is that we want to say that Z have some kind of similar behavior. So eventually, let me try to write down the expression for Z first. This is the partition function. And now we are saying that this thing should be dominated by the point where if we try to use the energy expression, then this form should be dominated by the energy at E star. So it should look like this. And the argument is simply, when you evaluate the expectation value of A, you are basically evaluating this integral. Okay, and if you just assuming that the expectation value A is not there, to some extent this integral is basically directly related to the integral of the partition function that you are evaluating. But anyway, the point is, once you notice this structure, you can consider this object, or you can connect this object with the thermodynamic potential, which is the Helmholtz free energy that we are familiar with. And then we can see that once we get the partition function in the canonical ensemble, actually we can get the Helmholtz free energy easily by taking the log from both sides of the equation. So I'll just write it down. So basically that's one of the very important connection, how to go from the canonical ensemble to the thermodynamic potential that we are familiar with. And once we know what is F, then we should be able to derive all other possible thermodynamic quantities. For example, you can try to evaluate the expectation value of the energy. Let's assume beta, which is the 1 over kVt, and you can show easily that if you take the natural log of your partition function and take derivative with respect to beta, it will look like this. Okay, that's basically the expectation value of the energy, but with the additional minus sign. Okay. So it should not be too hard. You just take the derivative with respect to natural log something, and then the something will be pop out downstairs, and you just do the chain rule. Then you will see this expression. Okay. So you can take a second derivative with respect to the natural log z and see what happened. And after some simple algebra, you can convince yourself it actually corresponds to the variance of your energy. And both of the object will be proportional to the system size. Both of them are going to be extensive. Okay. So if you try to think about this expression in another way, because we know that when we take the first derivative, it corresponds to minus e. So second derivative actually corresponds to, we are taking the derivative of minus e with respect to beta. And actually, if you do the chain rule again, you will see it corresponds to this expression. Okay. So at this moment, it is not super interesting because from the thermodynamics, we know this partial E, partial T is just the specific heat. But if we try to think about what we have achieved, you'll find it to be quite surprising, because let me just try to write down this important line. Okay. So what is the meaning of this equation? So at the left-hand side, what we are having is the variance of the energy. So this is actually a microscopic description of our system. It tells us that how the energy fluctuates around its mean value. Okay. This is basically a very microscopic. microscopic physics. Okay. On the right-hand side, basically we have temperature, Boltzmann factor, and specific heat, which is the macroscopic quantities that we measured in the lab. Okay. So when you're in the lab trying to measure the specific heat, what you are actually measuring is the fluctuation of the energy for the, for your system. So that's a very good demonstration that how statistical mechanics is trying to help you to understand what microscopic system is doing, right? Even though you are doing the measurement in the macroscopic world, this specific heat actually tells you in this microscopic world, the degrees of freedom will interact with each other in some crazy way. So the energy at the microscopic level will fluctuate in principle. But the specific heat tells you that how this energy fluctuates. Okay. And here we are actually derive a very specific example for something is called the fluctuation dissipation theorem. Okay. But now I think we should have a good picture about what canonical ensemble is. So we will try to use some more specific example to understand how to apply this kind of idea. Okay, so maybe I should put it here. Okay, so I think I'll just start by applying the canonical ensemble formalism to the ideal gas model. So for ideal gas model, we know the description of our system. Basically, the total energy is just sum over all the kinetic energy of our system, and they just live inside a box. Okay. So the partition function will now looks like this. Okay. So the 1 over n factorial is coming from the fact that we are discussing about indistinguishable particle. So there's a 1 over n factorial there. And the rest of the partition function correspond to the canonical formalism we just derived. So basically, we are trying to sum over all the possible microscopic configuration of our system. In this case, those configurations correspond to the position and momentum of our particle. And we need to specify what is the energy for a specific microscopic configuration. And in the ideal gas case, the expression for energy is relatively simple. You just sum up all the possible kinetic energy in different direction, x or y and z direction. Okay. So this is basically the partition function that we need to deal with. And because the energy is independent of the position, so we can do the integral in the real space easily. Then eventually we'll get just the volume of our system raised to the power of n, depends on how many particles we have. And then n factorial is still there. And the rest of the integral is related to the integral in the momentum space. And it should be a Gaussian integral. But before we do the Gaussian integral, we'll just write another step to express this integral. And the reason that we are able to do that is because we just factorize this exponential factor into each component, and we do the integral one by one. But because every integral shares the same expression, so we can just do it once and raise it to the power of 3n. Okay. And as I mentioned, this integral is a Gaussian integral, so it should not be a big problem for us to do it. So eventually, what we are going to get is n divided by n factorial and times the and here this lambda is the thermal debris wavelength. Okay. So the important step going from here to here, basically from the first line to the second line, is that there's no interaction between the particles. So this exponential factor can be easily factorized into a bunch of independent integrals. So as we mentioned, once we know what is the partition function, it should be easy for us to evaluate the Helmholtz free energy. You just take a natural log of your partition function. And in this case, you would look like this. Here we use and Stirling's approximation. Okay. I'm going to skip a lot of the steps because I think we have done Stirling approximations in several scenarios. So I'll just write down the final result. So to some extent, the only point that I want to emphasize is that usually in the ideal gas model, we assume that the volume occupied by each particle is much larger than the wavelengths, much larger than the volume formed up by the Broglie wavelengths. So what does that mean? It means that if you have a box, and because you have n particles, so maybe your system will be divided in little various different little boxes. Okay. So this is basically the volume occupied by each particle. But at certain temperature, the particle has the Broglie thermal wavelength that's described by this parameter lambda. So basically, you can imagine the particle already have some kind of intrinsic volume that's given by the thermal fluctuation. And we assume that at the ideal gas model, actually this volume is small compared with the volume or the average volume that's occupied in this box. So basically, we are assuming. Let me just zoom in this part, and we assume that the thermal wavelength is much smaller than this length scale given by the ratio between the volume and the particle number. And why it is so? Because we, at the ideal gas model, we assume that there's no interaction between those particles, which means that those particles should not see each other in that limit. Okay, so basically, once we know what is the free energy, then we got everything basically, because we can derive the entropy by taking derivative with of our Helmholtz free energy with respect to temperature, and the pressure is basically taking the Helmholtz free energy with respect to the volume with other extensive variables to be fixed. And I'm not going to do that in front of you because it should be something that's really straightforward. So now I think we have went through a simple example about how to apply canonical ensemble to the ideal gas model. Now I'm going to discuss a more important idea, which is the generalized ensembles. Okay, so we start from microcanonical ensemble, which has a fixed value of energy, and we said that it is not very practically useful because we don't have isolated system in real world. In the lab, usually what we can control is the temperature, so we want to develop a ensemble theory for fixed temperature. That's why we discussed the canonical ensemble in the last lecture. Now I'm going to tell you there's a way that you can systemize this procedure. Maybe in the different kind of scenario, you might have other control parameters. Then the question you will have is how to form an ensemble theory under different physical conditions. So I'll try to define the setting. So basically, the idea is very similar to the canonical ensemble case, but now we just try to abstract the idea in the following way. So suppose we have a reservoir with fixed intensive quantity Fi. Okay, so this intensive quantity Fi is defined in the following way. You take the derivative of your the entropy of the reservoir with respect to certain macroscopic quantity Xi, which is extensive, then you will be able to have a well-defined intensive quantity Fi. Okay, and here this minus sign is just for convention, but I'll just leave it there, and you'll see why I use this minus sign. So we can just try to think about the canonical ensemble. So in the canonical ensemble, this to some extent this Xi is the energy, because now we allow the reservoir to have a fixed temperature. Let me write it down. And by definition, we know in the canonical ensemble, this Fi is just a constant, it's -1. Okay, because the derivative of entropy with respect to energy is basically 1/T. Okay, so in the canonical ensemble, we said that the system can exchange energy. So in this generalized setting, we try to make similar argument. We said that the system now can exchange extensive quantity Xi with the reservoir. Okay, so let me try to write down some list such that we have a rough feeling about what we are doing. So canonical ensemble, we said that xi is energy and fi is some constant as -1. Okay, and since we might be able to discuss something like that, basically some a system that can exchange volume with the reservoir. For example, you have a piston or something. Then the corresponding intensive variable for that process is related to the pressure, which is minus P. If we try to take a look about how we define pressure in the previous chapters or previous lectures. So also you could have situation that the reservoir can exchange particles with the system, okay? And in that case, the corresponding conjugate variable is the chemical potential mu, okay? So of course, the list can go on. So the question is how to construct the corresponding probability description. So we can try to think about how we do our derivation in the canonical ensemble. So we start from the expectation value of A, and we said that, the microscopic, the microcanonical ensemble tells us that we should write our expectation value formally in this way. Okay. The process is basically exactly the same as we did in the canonical ensemble. So we said that, okay, so now we want to evaluate this phase space integral, but now we know that the system can exchange some extensive quantity xi with the reservoir, but the total xi for the system and the reservoir still should be conserved. So we can change this integral expression into this way. Oops. Okay. This is almost the same. In the previous lecture about the canonical ensemble, this X is just the energy. Okay. Or in the previous expression, it should be H. Okay. But now we are trying to make a general version of that. So we just stick with X. Okay. So following completely the same argument, we said that this is basically the phase space volume for the reservoir with the condition that its energy is specified by the total xi and the system's xi. So I'll just express it using this way. Okay. So again, as we mentioned, that the reservoir is a gigantic object. So the xi, the total xi actually is much larger. Oops, I think I've write something wrong. It should be systems. The total x should be much larger than the system's extensive variable x. Okay, so again, you just do the expansion around this xi, and you'll see. Okay, so here I express it using the intensive variable because at the very beginning, we assume that this is the quantity that is kept fixed for the reservoir. Okay. So yeah, so that's it. Again, we see the vector that is related to our probability is of similar form as the Boltzmann vector. But now this Fi and Xi have been generalized to other conjugate pairs. Okay. So the generalized partition function for this system should be interpreted in this way. And if it is the discrete version, should be just the regular summation. Okay. And the probability of C should be just the maybe I should not write this because now we so this is the expression for generalized ensemble about the probability distribution for the microscopic configuration. So similar argument we can also try to approximate the partition function by okay. So this is exactly the same argument we are trying to do in the canonical ensemble, that we try to re-express the integral of microscopic configuration CS, but now try to collect them according to the extensive variable that we want to generalize. Okay. So in the canonical case, this X corresponds to the energy. Okay. But in this case, we try to make it abstract. Then again, this integral can be considered as some microcanonical picture that this is actually counting the phase space volume that is accessible by the microscopic configurations such that it satisfies its extensive variable is X. So this integral eventually will look like this. Wait a second. Then again, we want to evaluate this integral, but as we mentioned, that the exponents will grow exponentially fast. So we want to use the saddle point approximation. to determine what is the corresponding value of x star. So 0-point approximation tells us that that corresponds to the condition that's given initially. So the generalized ensemble, the generalized ensemble therefore can be approximated by this exponential factor evaluated at the equivalent value of the extensive variable xi. Okay, and this thing usually is called the SU functions, and it is actually the Legendre transformation. Okay, so basically we are doing exactly the same thing as we did in the canonical ensemble, but we are just trying to generalize it to a more abstract way, such that we can adjust which ensemble we should use under different physical situations. Okay, so I think we'll stop here, and after 20 minutes break, we will continue our discussion about a specific example, which is the grand canonical ensemble, and then talk about the example using the ideal gas model. Okay, so see you after 20 minutes. Okay, so I assume that we are back online. Just a second, let me just try to make sure that, yeah, I think the audio is fine. Okay, so hi everyone, we will continue our lecture. So basically in the last lecture, I tried to went through the derivation of generalized ensemble in a relatively quick way, because I think the argument and the logic is completely identical with the canonical ensemble. The only difference is that now we try to make an abstraction about the idea to replace the exchange of energy with the concept of exchange of extensive variables x. Okay, so because of that, you can get basically everything, and also get the generalized thermodynamic potential as if we are doing the Legendre transformation of the energy. So, okay, so that's basically the idea. So let's try to use this generalized ensemble idea and try to apply it to a specific condition that we are interested in. So one of the example is the grand canonical ensemble. Oops. Okay. So now we are going. After we generalize it, we are going to talk about a specific example, such that we know what we are doing. So the first thing is that we consider our reservoir to provide a specific chemical potential. And what does that mean? It means that the reservoir can actually exchange particles with our system S. Okay, and the chemical potential is fixed. What that means is that from the definition of chemical potential, the value mu and the temperature T are all fixed. So from this expression, if we try to went back to the definition of the generalized ensemble that we just discussed, we said that the intensive variable is fixed by this given relation, and xi is the extensive variable that is allowed to be exchanged. Then in this scenario, the exchange, the object is the particle number. So xi is just the particle number n. And the fi is the corresponding intensive variable. And in this case, it is just the chemical potential mu. Okay. So now we can ask, in this particular setting where the system is allowed to exchange particles with its reservoir, how to construct the probability distribution, or how to construct the corresponding ensemble. And because this ensemble is used quite often, so it got a name. It's called the grand canonical ensemble. And now I'm just directly write down the conclusion if we just follow the generalized ensemble construction we just showed. The expectation value of the observable A can be evaluated by this expression. Okay, so here we basically just follow exactly the same expression that we are trying to evaluate the observable A using the microscopic configuration, but with the particular weighting factor. But in this case, we are discussing about the generalized concept. So we put the extensive variables and the corresponding intensive variable into our expression of the generalized ensemble. Then you will see this Boltzmann factor now is replaced with this additional term of chemical potential times n. Okay, and because we need to sum over all the microscopic configuration, in addition to those continuous variable Cs, we have some discrete variable. That's basically the number of particles in our system. Okay. So that's why there's a discrete summation outside this integration. And so that's it. That's how we evaluate the observables in this grand canonical ensemble setting. And the corresponding grand canonical partition function, which correspond to the partition function, which is the normalization factor for this particular exponential factor, actually can easily be derived, and it should be something like this. Okay. And as we have discussed previously, this exponential factor, basically we need to integrate over all the microscopic configuration called Cx, but it is not usually doable. So we can try to find a settle point approximation and approximate this partition function by this expression. And this will be left as an exercise because we've done that several times now. And here I'm just going to make another explicit connection of this expression with the thermodynamic potential omega. And this omega is what we have learned in thermodynamics. It is just the minus PV that correspond to the thermodynamic potential for the grand canonical ensemble. Okay. Then as usual, you can try to evaluate the expectation value of the energy by taking the derivative of nature log function with respect to this quantity, which is minus beta. And similarly, you can evaluate the particle number expectation value. And basically, that's something that should be quite straightforward once you know how to do that. So in order to be more specific, we'll try to discuss a particular example again, basically the ideal gas situation. Now we assume that this ideal gas is in contact with some big reservoir that can exchange particle with our system. So you can imagine that particles can go from the reservoir to our system, and the system is some kind of ideal, just a bunch of gas atoms that is bouncing back and forth. Okay. So usually, following the procedure, as we already learned, that there's no problem that we can write down the formal expression for the grand canonical ensemble of our ideal gas model in this scenario. But now this grand canonical ensemble will contain several parameters. First, the temperature will be there because we assume that it is reaching some thermal equilibrium, and also there will be a chemical potential that we need to specify our system because now it is in contact with a big reservoir with fixed chemical potential. But also, we assume that the system did not exchange volume with the reservoir, so we should have a specific parameter to specify the volume of our system. Okay, so the logic is that we might get this thing, and once we are able to get this grand canonical ensemble, then we said that, oh, basically we can get everything we want because, for example, the expectation value of the particle number can be evaluated by simply taking the natural log of this grand canonical ensemble partition function with respect to the corresponding intensive variables. Okay. So, of course, there are so many of them, but most of the time, as I said, even though we consider the system can exchange particles with the environment, but we still want to have some interpretation or some idea when the situation is that we know the particle number of our system. So usually once we derive this relation, what we can do is that we can invert this relation and try to express the chemical potential as a function of the particle number, temperature, and volume. Why it is useful? Because once you have this expression, then you are able to stuck that back into the partition function, then all the expression or all the observable that you are calculating will now be a function of the particle numbers. So that will be convenient, or that can reach our goal. So let's try to use the ideal gas case for the grand canonical ensemble. So let's just follow the strategy. First, we write down the grand canonical partition function for our ideal gas system. Okay, so we need to consider all the possible configurations. So basically, we sum over all the possible particle numbers, and there's a part of the exponential factor that's related to the chemical potential and particle number explicitly. We'll just take it out. Then we need to consider the partition function under the condition that particle number is fixed. That's basically when we have the n particles, we know that because they are indistinguishable, so we have this 1 over n factorial, and then we need to sum over all the possible microscopic configurations of our system. With the Boltzmann factor. Okay. So that's the grand canonical partition function that we had. So this part is basically the partition function. Oops. With fixed particle number n. Okay. And this is the under the canonical ensemble picture. The whole partition function is the grand canonical one. But when you write it down formally, you'll see that it is related to the canonical ensemble expression. Okay. And because this exponential factor related to the chemical potential is so frequently encountered, so people call this factor a specific name. That's basically you can define Z, which is called the fugacity by this expression. This is the fugacity. Okay. So if you use the fugacity to define your grand canonical partition function, you'll see it basically looks like like this. Okay. And if you try to keep the 1 over n factorial, it will be an interesting expression that you will see. This grand canonical partition function can be expressed like that. So here we use the information we got previously, that this Zn, which is the partition function under the canonical ensemble, actually correspond to this expression. Okay. So why it is useful? Because this thing basically is an expansion of the exponential factor. So this is the spatial structure for this ideal gas model, but it allows us to see how things work. So now we have a really nice expression for the grand canonical partition function. Then one can derive the thermodynamic potential basically. And we can just plug this expression inside. And natural log of the grand canonical partition function will actually correspond to this thing. Okay. So at this moment, if we want to express the equation of state using the chemical potential, this should be enough, because this Z is the fugacity, which is just exponential chemical potential divided by kBT. Okay. But as I mentioned, most of the time we don't want to express that, express the state equation using the chemical potential. So maybe we want to have a fixed particle number. So how should we do that? So one simple way is that you try to evaluate the expectation value of your particle number, which is now fixed, and it should be related to the grand canonical ensemble partition function, and taking derivative with respect to the intensive variables mu divided by kBT. Okay. And because the grand canonical partition function has a very special form, which is this exponential factor, once you take the take the derivative, you will find it basically is ZV divided by lambda cube. This line I kind of skipped through, but it should be easy to derive if you try to follow the expression of the grand canonical ensemble. So why it is useful? Because it just says that this vector actually is actually the total particle number n. So eventually what you got is the ideal gas state equation through the grand canonical ensemble. Okay. So at this moment, it is quite interesting to try to think back about what we have done, right? So we start from microscopic description, and then from the Boltzmann's postulate, we said that we want to evaluate some of the average value for our system because we want to study the statistical property of it. And we said that using the Boltzmann expression, it is very reasonable that we can give every microscopic configuration weight that's equal with each other. And the average is simply we just average over all these microscopic state with equal weights, and that's it. And that picture is basically the microcanonical ensemble. And then we said that most of the time, it is very convenient for us to study our system with fixed temperature. So what we want is that we want to have a heat bath or a reservoir that is in thermal contact with our system. Then we raise the question, if it is the situation, how one should develop a statistical description about the system. And we said that, yeah, there's a equivalent description starting from the microcanonical ensemble. And then the modification under the fixed temperature condition is quite simple. What you need to do is that you average your observable, but with the weight that is proportional with this Boltzmann factor. Okay, and this is basically the spirit of canonical ensemble. And through the derivation, we realized that, the argument that we derived the canonical ensemble actually can be generalized into a more bigger settings. So you don't need to only restrict to the situation that you can only use the temperature to describe your system. You might be able to use a fixed chemical potential or fix the pressure to describe your system. Just following through the identical argument. That's basically the idea for why we introduced this generalized ensemble. And the price we pay is basically similar, that in addition to the Boltzmann factor, you have another correction that's related to the product of your extensive variable and the intensive variable that you want to keep fixed. And that actually corresponds to the Legendre transformation of the thermodynamic potential. Okay. So everything is connected. So now we use a very specific example, which is the grand canonical ensemble to construct the corresponding partition function and the state equation for the ideal gas model. And we show that, yeah, indeed, we can derive the grand canonical partition function for this ideal gas model explicitly, and we can also reconstruct the state equation, PV equal to NKVT, using this grand canonical ensemble idea. So that's basically the whole story for the ensemble theory, and that all came from the very simple one assumption, basically the Boltzmann postulate. So once you postulate your entropy to be related to the phase space volume by this S equal to KB times nature log phase space volume, then you naturally got all this set of theoretical framework that can describe the statistical property for your system. Okay, and today we also show another very important idea, that is the fluctuation dissipation theorem. Basically, we show that the thermodynamic measurement, for example, when we are measuring the specific heat, actually there's a microscopic interpretation related to it, and it is related to the fluctuation of the energy. And this idea can also be generalized in other situations, because specific heat can be defined under different conditions. Then in that sense, then we are measuring the fluctuation of other extensive quantities. So that's one interesting observation, that actually statistical mechanics tells us something about the microscopics. Okay, so I think that will be today's lecture, and I think I will just leave the Gibbs formula for entropy and the free particle systems for the next lecture. And the rest of the time you can ask me about the questions or the homework questions, because I think it is very close to the midterm exam. And the range of the midterm exam basically will be, to today's lecture. About the last part is about this grand canonical ensemble, and also related ideas about how to construct ensembles under different situations. So I think that's it. And if you have further questions, you can ask me. If not, try to prepare your midterm exam. And also remember, homework 3 is due on the same day of the midterm exam. So please also try to finish that. Okay, so see you next week.